Milling. Milling operations are often completed before or during oral solid dose processing. Milling of dry powders can be broadly classified into two main types: low energy milling and high energy milling. The most frequently used low energy milling technique is co-milling. The goal of co-milling is to delump powders to ensure a uniform powder flow and also to ensure that dosage content uniformity is maintained. For certain crystalline materials, co-milling can also be used to directly reduce particle size. Co-milling can be applied in a number of settings. Only the API is co-milled. Only the excipient or excipients are co-milled. Mixed API and excipients are co-milled as a pre-blending step. Co-milling can be applied following an extended static period prior to tablet compression or encapsulation. Co-milling equipment, such as a Witron Quadro co-mill, consists of a small conical chamber where a powder is forced through a conical screen by a rotating impeller. The impeller induces centrifugal acceleration of the powder and is the driving force behind the delumping step. Particles that are sufficiently small transverse through the screen pores. Larger particles or lumps are size reduced via shear between the impeller and the screen surface. Control of co-milling is achieved through selection of screen size holes, micrometers up to millimeters, impeller speed, and impeller design. Design of a co-milling process must incorporate a clear understanding of the agglomerate nature of the powder that is being processed, as the unit operation has insufficient energy to break hard agglomerates. High energy milling. High energy milling, or impact milling, is usually completed in a mill with rotating hammers or pins. This unit operation usually reduces individual crystal particle size through mechanisms of chipping, fracture, and breakage. Often, the goal of impact milling is to reduce the particle size distribution such that the increased particle surface area enhances product dissolution, thus modifying drug availability. Impact milling may also be applied to generate a uniform particle size distribution to ensure powder flow consistency. Control of milling is usually determined by the energy input to the mill speed, and also the residence time of powder in the milling zone. Jet milling. In the biopharmaceutical classification system, Class 2 and 4 drugs are low solubility APIs. For very low solubility APIs, milling to a low micron particle size distribution can mitigate the solubility hurdle by enhancing the overall API surface area. For sub-micron particle sizes, it becomes unfeasible to isolate such small particles by conventional pharmaceutical isolation techniques. For sub-micron particle size distribution requirements, jet milling is usually the preferred milling option. The operation of a jet mill is conceptually straightforward. Powder is slowly fed into a milling chamber where compressed gas, which can be air or nitrogen, rapidly accelerates the particles in a vortex. Particle size reduction is mediated by particle-particle collisions. Jet milling usually provides a highly uniform particle size distribution as particle classification is embedded into the operation of the mill. This is achieved as the larger particles are maintained in the outer attrition zone of the mill through centrifugal force. As particles are micronized, they graduate to the center of the mill where they are discharged from the milling zone. No grinding forces are involved in this milling operation. Therefore, jet milling is highly suited to thermally sensitive materials as there are no mechanical moving parts and any heat generation is dissipated by the large gas flow.